Welcome back to the sleepy universe, where stories of science are told slowly in the quiet stillness of the night. You can let your body relax, allow your breathing to become more even, and begin to drift away from the familiar sounds around you. Tonight, we will travel far back through cosmic history, to an age before the sun, before the Milky Way, and before any star shone brightly enough to break the darkness. It was there that the story of every galaxy, every planet, and even the atoms now within our bodies began with differences so small they were almost impossible to detect. There was a time when the universe had not yet taken on the familiar shape it has today. There were no spiral galaxies extending luminous arms through space, no galaxy clusters gathered around vast gravitational regions, and no enormous voids stretching across hundreds of millions of light years. Matter was already present, and space was already expanding, but almost no structure existed clearly enough to be given a name. In every direction, the young universe stretched outward with remarkable uniformity, like a boundless layer of hot, glowing mist in which each region closely resembled countless others around it. Had that uniformity been absolute, everything that followed might have unfolded very differently. Gravity would still have existed, but there would have been no distinct place for matter to begin gathering. Every particle would have been pulled almost equally from every direction, causing the forces to nearly balance one another. No region would have held an advantage from which to become the first center of concentration. Nowhere would have been dense enough to retain more gas, and no gravitational wells would have gradually deepened over time. As space continued to expand, matter might simply have grown more diffuse, leaving behind an immense universe with almost no stars, no galaxies, and no worlds complex enough to one day look back toward their own origins. But the early universe was not perfectly smooth. Hidden within that nearly uniform distribution of matter were extraordinarily small variations. Some places contained slightly more matter than average, while others contained slightly less. The differences were so subtle that, had we been able to look upon the universe with ordinary eyes, we would not have seen any clear boundaries or recognizable forms. There were no immense clouds separated from their surroundings, and no prominent concentrations of matter standing out against the background of space. There were only faint ripples concealed within a universe that was still hot and dense, with variations of roughly 1 part in 100,000. 1 part in 100,000 may sound far too small to determine the fate of an entire universe. Add a single drop of water to a broad lake, and the surface appears almost unchanged. Place one more grain of sand upon a beach, and the shoreline keeps the same shape. Yet gravity does not require a large difference at the beginning. It needs only one place with slightly more matter than its surroundings, along with enough time for that early advantage to accumulate. A region that was a little denser would exert a slightly stronger gravitational pull. That small difference would allow it to draw more matter inward from the space around it. As additional matter arrived, the density of the region increased, and its gravity became stronger than before. A self-reinforcing process began. Places with more matter pulled more strongly, and the stronger pull brought in still more matter. There was no single moment when everything suddenly changed. At first, the growth was so slow that it would have been almost impossible to notice. But each time matter shifted toward a denser region, the contrast between that place and the surrounding universe became a little greater. During the very early universe, temperatures were still too high for stable atoms to form. Light could not travel freely through space, because it was constantly colliding with electrically charged particles. Matter and radiation moved through a dense environment, while space continued to expand and the temperature gradually fell. Amid all this motion, gravity continually responded to differences in density. It did not create new matter, nor did it know in advance where a galaxy would appear. It simply drew matter toward places where slightly more matter was already present, patiently deepening ripples that were almost too faint to see. Over millions of years, those small differences became more distinct. Over hundreds of millions of years, some regions began to retain vast quantities of gas. Where the density became high enough, The gas was compressed, grew warmer, and gradually lost energy, preparing the way for the first stars to appear. Over billions of years, smaller structures continued to merge and attract more matter, forming galaxies, galaxy clusters, and systems of ever-increasing size. What had once been only a tiny variation in the early universe eventually became regions containing trillions of stars. Places with less matter changed in a different way. As gas and dark matter gradually left the thinner regions and flowed toward denser ones, those regions became even emptier. Great voids expanded, while matter gathered into sheets, filaments, and dense knots. From a universe that had once been almost uniform, an enormous network began to emerge, with galaxy clusters forming where multiple streams of matter met and vast dark spaces stretching between them. Today, when we observe space on a sufficiently large scale, evidence of that process can be seen everywhere. Galaxies are not distributed at random like dust scattered evenly across a flat surface. They gather into groups and clusters, and extend along filaments of matter far beyond the portion of the universe visible to the unaided eye. The Milky Way does not exist in isolation within empty space. It belongs to a much larger environment, influenced by neighboring galaxies, and by a network that began taking shape before the first star ever appeared. The atoms that make up our bodies formed much later than those earliest stages. Carbon, oxygen, calcium, and iron had to be created inside stars and then scattered back into space as those stars changed or reached the ends of their lives. But before any star could produce those elements, gas first had to find places where it could gather. Before gas could gather, gravitational wells had to form. And before those gravitational wells could exist, the universe had to contain tiny variations in the way matter was distributed. The history of every structure, then, did not begin with an enormous object, but with an imbalance that was almost invisible. Within the ancient light that still fills the universe today, those first ripples have left behind a trace. They belong to an age when there were no galaxies to observe, yet the conditions required for galaxies to form were already present. By measuring the smallest variations within that ancient light, science can follow the path from a universe with almost no shape to stars, planets, and a network of galaxies extending across billions of light years. It was a construction without a predetermined blueprint, without a single center, and without an architect standing outside the universe to arrange it all. The shape of the cosmos grew as matter responded to the presence of matter itself, while time and gravity caused tiny variations to deepen. Every brilliant structure we see today can be traced back to a time when the universe was almost perfectly uniform, yet retained just enough unevenness for change to begin. That slight imperfection opened the way for gravity to begin its work across billions of years, transforming faint ripples into clouds of gas, turning gas into stars, gathering stars into galaxies, and connecting galaxies into the immense network that surrounds us in the darkness of the night. When the ancient light was finally able to separate from matter and travel freely through space, the universe left behind a faint map of its earliest differences. The slightly denser regions were not yet galaxies. They had no clear form and were not massive enough to hold the vast clouds of gas we might imagine today. They were simply places containing a little more matter than their surroundings, but those delicate variations were enough to send different regions of the universe along different paths. Ordinary matter, the substance that would later become gas, stars, planets, and living bodies, could not immediately fall deep into those denser regions. During an earlier period, it had been tightly coupled to light. Photons repeatedly collided with free electrons, creating pressure that resisted compression. Gravity tried to draw matter inward, while radiation pushed it outward, causing the primordial plasma to oscillate rather than collapse freely. Even after neutral atoms began to form and light escaped, ordinary gas still needed time to cool and fully respond to the gravitational wells that were gradually deepening. But not all matter in the universe shared the same history with light. There is a component that does not shine, does not absorb light in the familiar way, and does not experience radiation pressure as ordinary gas does. We call it dark matter, a name that says more about the limits of human observation than it does about its true nature. Dark matter is not dark because it is black. It is dark because, so far, we have not seen it emit, reflect, or block light clearly enough for conventional telescopes to detect it directly. If we relied on light alone, dark matter would leave almost no image behind. But gravity does not need light to recognize mass. Anything that carries energy and contributes to a gravitational field can influence the motion of other things, whether or not it shines. It is through those effects that this invisible component gradually reveals itself in our measurements. In the early universe, the difference between dark matter and ordinary matter became especially important. While the plasma remained locked in oscillation by photons, dark matter was not carried along in the same way. It was still affected by cosmic expansion, still moved under gravity, and still preserved the original variations in density. But light did not resist its collapse as strongly as it resisted the collapse of ordinary gas. Regions containing slightly more dark matter began drawing in additional dark matter from their surroundings, allowing the original differences to grow. This process did not happen quickly. During the era when radiation dominated the universe, radiation pressure and the rapid pace of expansion limited the growth of many structures. Dense regions could not immediately contract into large clumps. But as the universe continued to expand and cool, the energy density of radiation fell more rapidly than the density of matter. Gradually, matter became the dominant influence on the large-scale growth of structure, and density variations that had once been extremely small gained more time to develop. Imagine a vast region of space where the density of dark matter is only slightly higher than in the surrounding areas. There is no clear boundary marking where this structure begins or ends. No solid surface encloses it, and no fixed, unchanging center defines it. Dark matter particles pass through the region along many different paths. Some sweep through and move on. Some remain bound for longer periods, and many others continue falling in from the surrounding environment. Over time, their combined motion creates a region of enhanced density, commonly known as a dark matter halo. The word halo can easily suggest a shell surrounding a galaxy, but the true structure is not like a container or a sphere with a clearly defined outer surface. It is a region of space where dark matter is more concentrated than average, while the particles within it remain in constant motion and continually exchange gravitational energy. The density is usually higher near the center and gradually decreases with distance, but there is no natural boundary like the surface of a planet. A galaxy may later form deep within this halo, while the halo itself extends far beyond the luminous region of stars visible to the human eye. The first halos did not appear as enormous structures. In current models, smaller regions could collapse first, then attract more matter or merge with one another to create larger halos. This is a hierarchical process of growth. Smaller structures do not simply disappear when they merge. They may leave traces behind as substructures, streams of matter, and complex patterns of motion within the larger system. If dark matter were visible, the universe at that time might not resemble an empty darkness. Instead, it might appear as a landscape slowly taking shape, with deeper depressions forming among relatively level regions. But this landscape would not remain still. Each depression would continue attracting matter, shifting and changing shape under the influence of nearby structures. Halos approaching one another could exchange matter, stretch each other's forms, and eventually merge into a larger system. Dark matter is often compared to an invisible scaffold upon which galaxies are built. That image helps convey its supporting role, but it can also be misleading if taken too literally. Scaffolding in a building is assembled according to a plan, given a defined shape, and left waiting for materials to be placed in their proper positions. The framework of dark matter has no predetermined design, nor does it wait for the universe to fill it. It forms on its own, changes shape, and continues growing under its own gravity. Ordinary gas later falls into these structures, but as the gas cools, forms stars, and releases energy, it can also affect the surrounding environment in return. Dark matter, then, is not a rigid mold forcing every galaxy into the same form. Two halos with nearly identical masses can still contain very different galaxies, depending on how much gas they receive, their histories of mergers, their rates of star formation, and the influence of stellar explosions or central black holes. Dark matter provides the initial gravitational foundation, but the visible universe is shaped by many other processes unfolding within that foundation. Although it cannot be seen directly, the presence of dark matter is revealed through many independent lines of evidence. Within galaxies, stars far from the center move faster than they should if all the mass came only from what is visible. If only the observed stars and gas were present, gravity in the outer regions would be too weak to hold those stars in the orbits we measure. This suggests that a galaxy is embedded within a much larger mass, spread far beyond its bright stellar disk. In galaxy clusters, the missing mass becomes even more apparent. The member galaxies move through their shared gravitational field at speeds that indicate the cluster contains far more mass than the total amount of observable stars and gas. The hot gas between galaxies also reaches temperatures and distributions that require a deeper source of gravity. Even when every luminous component is added together, there is still not enough mass to explain how the cluster remains bound. Light from extremely distant galaxies provides another way to measure this hidden mass. As light passes near a region containing a great deal of mass, its path bends. If the mass is large enough, background images may be stretched into arcs, repeated, or distorted, even when the bending is too subtle to detect around a single galaxy. Measurements of millions of galaxy shapes can reveal how matter is distributed across the sky. The resulting gravitational maps often show that mass is both more abundant and more widely spread than the luminous matter alone. No single measurement tells the entire story. The motion of stars suggests that galaxies appear to be missing mass. The motion of galaxies and hot gas shows that clusters face the same problem. Gravitational lensing allows mass to be mapped without relying on light emitted by the matter itself. When these clues are considered alongside the structure of the cosmic microwave background and the large-scale distribution of galaxies, a consistent picture gradually emerges. Most of the matter contributing to gravity is not the kind that forms stars, planets, or human beings. This does not mean the nature of dark matter has been solved. We still do not know with certainty what kind of particles it is made of, whether it consists of one type or several, or whether it interacts with ordinary matter in some extremely weak way beyond gravity. Many experiments deep underground, in orbit, and inside particle accelerators continue searching for a direct signal, but no result has yet been accepted as the final answer. This uncertainty does not make the gravitational role of dark matter arbitrary. It is possible to measure an object's mass and influence without knowing what it is made of. A distant planet can be inferred from the motion of its star before light from the planet itself is ever detected. In much the same way, dark matter is recognized through the way it moves stars, holds galaxy clusters together, bends light, and influences the growth of structure across billions of years. During the age before any stars existed, small halos continued to deepen within an expanding universe. They gave off no light to mark their locations, and they did not yet contain brilliant stellar disks that could be seen from far away. Even so, within that darkness, the universe had already begun dividing into regions with very different futures. Some would continue drawing in matter and become the centers of large galaxies. Some smaller halos would be absorbed into larger systems, losing their outer layers while leaving behind substructures within them. Less dense regions would gradually lose matter and expand into the great voids between the filaments of the cosmic web. Once atoms had formed and radiation pressure no longer held the gas in its earlier state, ordinary matter began to respond more clearly to this invisible gravitational landscape. Hydrogen and helium had no way of knowing what dark matter was but they reacted to the pull created by its mass. Gas began moving toward regions that had already been prepared, falling into halos and gathering where the gravitational wells were deepest. That fall was not gentle. Streams of gas arriving from different directions collided, compressed, and heated up. Part of their motion was converted into heat, allowing the gas to resist further contraction for a time. To move closer to the conditions required for star formation, the gas had to find a way to release energy and become cooler. Because the universe at that time contained almost no heavy elements, the available paths for cooling were extremely limited. Yet even before the first source of light appeared, something important had already been established. Fluctuations that had once been no more than faint differences in the early universe had now grown into real gravitational regions. They were not yet galaxies, and they did not yet contain stars, but they had created invisible basins into which gas could begin to fall. In a universe without starlight, the most important work was taking place where nothing could be seen. Dark matter continued to gather, halos continued to merge, and gravitational wells continued to deepen. Then clouds of hydrogen and helium began drifting into them, carrying the potential to create every source of light that would appear later. The darkness was no longer an empty expanse in which nothing happened. It had become the place where matter was slowly finding its way toward the first centers of concentration, preparing for the moment when gravity would not only create invisible structures, but would finally help part of the universe begin to shine. After the first atoms formed and light could travel freely through space, the universe became transparent, but that transparency did not yet reveal a sky filled with stars. No sun rose above a horizon, no planet moved through a pool of light, and no bands of galaxies stretched across the darkness. The glow left over from the hot early universe was still present everywhere, but as space continued to expand, its wavelengths were stretched, its energy declined, and that light gradually shifted beyond the part of the spectrum visible to human eyes. The universe entered a long interval often called the cosmic dark ages, not because radiation had disappeared entirely, but because no distinct sources of light, such as stars or galaxies, yet existed to break the night. Even without anything bright enough to mark the changes, matter continued to move quietly across vast regions of space. Dark matter halos kept drawing in more mass, and the gravitational wells formed from the earliest fluctuations grew steadily deeper. Hydrogen and helium, no longer tightly coupled to photons as they had been in the primordial plasma, began responding more clearly to this invisible gravitational terrain. There was no precise boundary where the gas suddenly changed direction, and no single moment when all matter began rushing toward one center at once. Far from a halo, a hydrogen atom would feel only an extraordinarily small imbalance between the pulls coming from different directions. But over millions of years, that imbalance was enough to bend its path gradually toward the denser region. Countless atoms moving in similar ways formed enormous streams of gas, flowing out of thinner regions and into the growing structures of dark matter. What had once been spread almost uniformly through the early universe now began gathering around gravitational wells, preparing for a process far more complex than matter simply falling to the bottom of a hole. Dark matter can pass through other streams of dark matter with almost no collisions in the familiar sense. But ordinary gas does not have that freedom. Hydrogen and helium atoms collide, change direction, exchange momentum, and convert part of their organized motion into heat. As gas falls deeper into a halo, gravity accelerates it. When streams arriving from different directions meet, they are compressed, producing shock waves and turbulent motion. The gravitational energy is not lost during the fall. It is transformed into thermal energy within the gas, causing the particles to move faster and increasing the pressure. Here, a natural difficulty appears. Gravity is what draws matter together, but the fall itself heats the gas, and hot gas tends to resist compression. If the pressure becomes strong enough, the cloud can temporarily stop contracting and remain inside the halo as a hot, diffuse region, unable to reach the density required to form a star. To continue sinking inward, the gas had to find a way to release the energy it had gained. In the star-forming clouds of the modern Milky Way, this happens through many different pathways. Carbon, oxygen, cosmic dust, and complex molecules can absorb energy and radiate it away, helping the gas cool, reducing its pressure, and allowing contraction to continue. But the early universe contained almost none of these components, because few generations of stars had yet lived, created heavy elements, and returned them to space. Ordinary matter still consisted mainly of hydrogen and helium, with only a very small amount of lithium, which greatly limited the gas's ability to cool. Atomic hydrogen can emit radiation under certain conditions, but in many of the first small halos, the gas was not hot enough for this mechanism to work efficiently. In those cases, a component that made up only a tiny fraction of the gas became especially important. Molecular hydrogen formed when two hydrogen atoms bonded together. In the modern universe, tiny dust grains provide favorable surfaces on which hydrogen atoms can meet and form molecules. But in the age before stars, dust barely existed. Molecular hydrogen had to form through chains of reactions in the gas phase, a process that was much slower and less efficient. Only a very small fraction of the hydrogen became molecular, yet sometimes that small amount was enough to change the future of an entire cloud. When these molecules collided with surrounding particles, they could absorb energy, move into different rotational or vibrational states, and then release photons as they returned to lower energy states. Those photons escaped from the cloud, carrying away part of the heat accumulated during the fall and leaving the gas slightly cooler. As the temperature dropped, the pressure weakened, and gravity could once again pull matter closer together. At first, the change was so slow that it would have been difficult to notice. But each time the gas lost a little more energy, it could contract a little farther. As it contracted, the density increased, collisions became more frequent, and conditions inside the cloud continued to change. A large cloud of gas does not contract like a perfect sphere in which every part moves toward a single point at the same time. Within it, there are always regions that are slightly denser, streams moving at different angles, small vortices, and disturbances created as gas collides while entering the halo. As the entire structure contracts, gravity amplifies these small differences as well. A subregion containing more matter exerts a stronger pull than its surroundings, drawing in additional gas and gradually becoming a separate center of collapse. The same mechanism that once transformed tiny density variations into dark matter halos now repeats on a far smaller scale within the gas cloud, preparing to form stars. Instead of all the matter collecting into one central core, the cloud can break apart into several dense regions, each continuing to compete for gas from the shared environment. The degree of fragmentation depends closely on the temperature of the gas. The colder the gas becomes, the weaker its pressure, and the more easily smaller regions can be pulled inward by their own gravity. But molecular hydrogen cannot lower the temperature indefinitely. Its ability to radiate energy has limits, so primordial gas generally remained much warmer than the cold star-forming clouds found in the Milky Way today. In warmer gas, a region had to contain more mass before its gravity could overcome the internal pressure and continue collapsing. For this reason, the first stars are generally expected to have been more massive than most stars forming in the modern universe. However, this does not mean that every halo necessarily produced only one enormous star. Detailed simulations show that the gas could fragment into multiple cores, form rotating structures, and sometimes produce an entire group of stellar embryos. Some of these cores merged, some continued growing separately, and others lost access to gas as nearby regions developed more rapidly. Rotation made the path of matter even more complex. Streams of gas rarely entered a halo from every direction in perfect balance, and even a slight irregularity in their initial motion could leave behind a measure of angular momentum. As the cloud contracted into a smaller volume, its rotation accelerated. much like a spinning object turning faster as its mass is drawn closer to the axis. The gas could no longer continue falling directly toward the center. Instead, it gradually spread into a flatter structure, rotating around the dense region in the middle. Within this structure, gravity pulled matter inward while rotation held it in orbit. Spiral arms and turbulent regions within the gas could carry some angular momentum outward, allowing the material closer to the center to move deeper in. Dense cores, forming within the same region, not only attracted gas, but also pulled on one another, altered one another's paths, and turned the first environment of star formation into a dynamic system in constant change. As one core acquired enough matter and continued to contract, the density at its center increased by many orders of magnitude. The distance between particles decreased, collisions became more frequent, and the gas found it increasingly difficult to release energy through the processes that had worked at lower densities. A photon emitted near the center might no longer travel directly outward. Instead, it could be absorbed by the surrounding material and then re-emitted in another direction. As the core became increasingly opaque, heat remained trapped for longer periods, causing the temperature to rise more rapidly than before. Gravity continued pulling inward, while thermal pressure grew stronger and resisted compression. The contraction did not stop entirely, but it entered a slower and more complicated stage, in which each layer of gas responded differently to gravity, temperature, and the continuing flow of matter from outside. Viewed from a distance, such a halo would still have appeared almost completely dark. There would have been no clear point of light revealing how far the matter inside had traveled along the path toward becoming a star. But moving inward through each layer, the structure would gradually emerge. At the outermost edge lay the vast dark matter halo, where invisible mass dominated the gravitational field. Within it, streams of hydrogen and helium continued to fall inward, collide, and heat up. Closer to the center, some of the gas had released enough energy to contract into denser regions, while rotation created disks and spiral flows. Deepest of all were one or more small cores that were gaining mass, far hotter and denser than the primordial gas from which they had formed. The entire system was linked by gravity, yet each region moved on a different timescale, from gas streams in the outer halo changing over millions of years to much faster variations within the central core. Not every halo reached this stage. Some were too small to retain gas once it had been heated. Some failed to produce enough molecular hydrogen for efficient cooling. Certain halos were drawn into larger structures before their inner cores had time to contract, while others were disturbed by gas flowing in from the surrounding environment. Once the first sources of light began appearing elsewhere, their ultraviolet radiation could also break apart molecular hydrogen in nearby clouds, making cooling even more difficult. Star formation, therefore, did not begin everywhere in the universe at once. Some regions reached the necessary threshold earlier, while others remained in darkness, waiting for their halos to grow larger or for gas to gather long enough to overcome the obstacles within. In the regions that succeeded, matter continued falling onto the contracting cores, gradually increasing the mass at the center. The energy released by this accretion heated the core and caused it to emit radiation. But this faint glow was not yet the steady light of a star. It still came mainly from gravitational energy, released as gas descended through the gravitational field and was compressed into a smaller volume. Inside the core, hydrogen was no longer spread across immense distances as it had been before. The particles were forced closer together, moved more rapidly, and collided with increasing energy. Pressure at the center rose and temporarily resisted collapse, but matter from outside continued to arrive, strengthening the gravitational pull and keeping the process moving forward. For a true star to be born, the core had to reach conditions that allowed hydrogen nuclei to combine. Positively charged nuclei strongly repel one another, so bringing them close enough is not easy. Only when the temperature and density became sufficiently high could a small fraction of the nuclei approach within the range where nuclear fusion became possible. Before that threshold was reached, the core remained only a contracting structure, heated by gravity and fed by streams of gas from its surroundings. It had become entirely different from the diffuse cloud it once was, but it still lacked an internal source of energy capable of sustaining a long-term balance. Across most of space, the darkness continued. Other halos quietly merged, streams of gas kept drifting toward denser regions, and countless primordial clouds had not progressed beyond the earliest stages of contraction. But in a few rare places, the necessary chain of conditions was nearly complete. A tiny density fluctuation from the early universe had grown into a dark matter halo. That halo had retained hydrogen and helium. The gas had fallen inward, heated up, and then radiated some of its energy away. Within it, dense regions had formed, fragmented, and continued drawing in matter until a hot core emerged. Each step unfolded slowly, without any brilliant flash to mark it, and without a clear boundary separating one stage from the next. At the centers of those first cores, the temperature was still rising. Gravity continued pressing matter inward, while pressure tried to keep it from contracting too quickly. Hydrogen nuclei moved with increasing energy, sometimes passing very close to one another, before electric repulsion forced them apart again. Only a slight further change in the central conditions was needed for a source of energy unlike anything that had existed before to appear, no longer produced by the fall of gas, but by transformations taking place within the nuclei themselves. Outside, the universe still had no dawn. The ancient background radiation continued cooling as space expanded, while dark structures grew in silence. But deep inside a number of halos, matter had been brought close to the final limit of gravitational collapse. After tens of millions of years without stars, hydrogen was gathering in cores so hot and dense that the darkness could not continue in the same way forever. Inside a small halo in the young universe, a gas core continued contracting under its own weight. Matter from the outer layers kept falling inward, slowly increasing the central density and raising the temperature beyond anything that had existed in the original cloud. Hydrogen nuclei moved faster and collided more often, yet most were still deflected by electric repulsion before they could approach closely enough. For a long time, the core was heated only by gravity, through energy released as gas fell into an ever smaller region. Then, among countless collisions that led nowhere, a few nuclei began to come close enough to combine. A tiny fraction of mass was converted into energy, new reactions began to follow one another, and for the first time in cosmic history, a cloud of gas started generating heat from within itself. This change did not appear as a sudden explosion in space. The newborn star was still surrounded by dense gas, still gaining matter from the cloud, and still had not reached a stable state. Gravity continued pulling the outer layers inward, while energy from the core worked its way outward and created pressure in the opposite direction. These two tendencies gradually approached a temporary balance. Gravity sought to compress the young star, while heat and radiation from within resisted further collapse. After a journey that began with density fluctuations, almost too small to detect, matter had created a source of light capable of enduring by transforming hydrogen into helium. No one knows exactly where the first star appeared, and there is no reason to believe that only one star held that distinction across the vastness of space. Many halos may have approached the same threshold within relatively similar intervals on cosmic timescales, even though the distances between them remained immense. In some places, one dominant core captured most of the gas and grew rapidly. In others, the cloud fragmented into several stellar embryos existing together within a small region. Light therefore did not spread outward from a single center, but began to appear in scattered points, like distant sparks separated by enormous stretches of space that remained deeply dark. Those stars were made from matter far simpler than the material that formed the sundae. The original gas consisted almost entirely of hydrogen and helium, because carbon, oxygen, silicon, and iron had not yet been produced in significant quantities. The absence of heavy elements made it harder for the clouds to cool and to break apart into smaller pieces, as they do in modern star-forming regions. For this reason, models often suggest that many of the first stars may have been more massive and hotter than most stars forming today, although their exact masses and the full range of their diversity remain open questions. Some may have become enormous objects that consumed their fuel in a short time. Others may have been smaller than once imagined, especially if the disks of gas around them fragmented into multiple cores competing for the same supply of matter. Whatever their mass, the first sources of light did not exist in isolation from the environments that had created them. As energy from their cores passed through the surrounding layers and escaped into space, it encountered hydrogen that was still falling inward from every direction. The light heated the gas near each star, raised its pressure, and could slow the flow of accretion that was feeding the star's growth. Ultraviolet radiation could also break apart molecular hydrogen in nearby clouds, removing one of the few effective cooling pathways available to primordial gas. A small halo that had been close to forming stars might be forced to wait longer because a new source of light had appeared nearby, while the shining star itself could limit its final mass by pushing away or heating the remaining gas. Yet the effects of light did not always slow star formation. At the edge of a heated region, shock waves could compress other layers of matter to greater densities. Gas driven away from one place might gather somewhere else, creating new regions capable of collapse. The same source of energy could disperse one small cloud, keep another in a hot state, and yet help a more distant region grow denser. The outcome depended on distance, density, the mass of the halo, and how long the radiation acted. From the moment the first stars appeared, the formation of structure was no longer only a story of matter being drawn into gravitational wells. The objects created by gravity had begun to reshape the environments around them. Massive stars lived at a very different pace from smaller, longer-lasting ones. Their stronger gravity compressed their cores to higher temperatures, causing them to consume fuel rapidly. Hydrogen gradually became helium, and under the right conditions, nuclei continued to combine into heavier elements. Carbon and oxygen began to appear in a universe that had previously contained almost none of them. In stars massive enough, the process continued, creating different layers of matter, each carrying the imprint of temperatures and pressures that had once existed deep inside the star. The universe now had a new way to create complexity. Simple atoms were gathered by gravity into a hot sphere, and within that sphere, nuclei were rearranged into elements that had never before been common. Those new materials would have meant little to the surrounding universe if they had remained sealed inside stars forever. But the first stars, especially the massive ones, could not maintain their balance indefinitely. As the fuel in their central regions changed, their internal structures changed as well. Some may have ended in powerful explosions that hurled matter outward at tremendous speeds. Others may have collapsed more deeply and left behind black holes, sometimes releasing only part of their outer layers. Not every primordial star met the same fate, but as long as some of them returned transformed material to space, the environments in which new stars formed could no longer retain their original composition. A cloud that had once contained only hydrogen and helium now received carbon, oxygen, and other elements created inside stars. At first, the amount of heavy elements remained very small and unevenly distributed, because each explosion enriched only a limited region around it. Even so, a slight change in composition could open new pathways for cooling. Heavy atoms possess many energy states that allow them to radiate efficiently, while the first grains of dust could form within ejected material and provide surfaces on which molecules could grow. As gas became better able to lose heat, it could fragment into smaller regions, allowing lower mass stars to appear. Some of those small stars could live so long that they might survive through most of the age of the universe, while the generations before them had disappeared long ago. This transition did not occur along a clear boundary separating one era from another. Primordial gas and enriched gas could exist near each other, mix incompletely, and produce groups of stars with different compositions within the same broad region. A new star might form from a cloud that had received material from an earlier explosion, while in a more distant halo, nearly pristine gas was still collapsing for the first time. The universe did not move from simplicity to complexity all at once. The change spread from region to region, carried by gas flows and mergers, leaving behind an uneven landscape in which different generations of stars appeared across a long span of time. Energy from stellar explosions also changed the way gas was distributed inside small halos. Some material was driven away from the central regions, sometimes fast enough to escape the halo's gravitational hold. Low-mass systems were the easiest to disrupt because their gravitational wells were not deep enough to retain all their gas after a powerful release of energy. Star formation could pause until the gas cooled and returned, or until the halo drew in a new supply of matter from its surroundings. Larger systems held on to gas more effectively, but even there, the material did not remain still. It was heated, lifted away from the center, mixed with fresh streams flowing inward, and sometimes fell back again. From a very early time, matter in star-forming systems had already entered a cycle of gathering, shining, being driven outward, and returning. While individual stars transformed the space around them, the halos that contained them continued moving under gravity. Small halos approached one another, stretched each other's shapes, and merged into larger structures. Groups of stars that had already formed did not necessarily fall directly toward a common center. They could move along complex paths, pass through clouds of gas, and leave behind new dense regions. Whenever two systems met, gas could collide and lose energy, while dark matter and stars interacted mainly through gravity. The result was not an object that immediately became orderly, but a chaotic system of gas, stars, streams of dark matter, and sometimes newly formed black holes. These early systems did not yet resemble the balanced spiral galaxies often seen in modern images. They may have been small, distorted, and constantly changing, with bright clusters of stars scattered among uneven regions of gas. Matter flowed inward from the surrounding cosmic web, while stellar explosions pushed some of the gas back out. A newly merged halo could bring in additional stars and fuel, alter the direction of rotation, or disrupt a structure that had only just begun to form. Even without a stable shape, something important had appeared. Stars, gas, and dark matter were no longer concentrated only in separate regions, but had begun to coexist within gravitational systems capable of receiving more matter and growing over time. These were young galaxies, not complete islands in space, but developing nodes within a far larger network. Light from the first galaxies did not stop at the edges of their halos. Lower energy photons could travel through the intergalactic medium, while ultraviolet photons with enough energy were often absorbed by neutral hydrogen. When such a photon encountered a hydrogen atom, it could separate the electron from the nucleus, leaving behind a free proton and an electron moving on its own. Around each group of hot stars, a region of ionized gas gradually appeared. At first, these regions were small and surrounded by enormous amounts of neutral hydrogen. But as more stars formed and more young galaxies began to shine, the bubbles of ionized gas started to expand. On the largest scales, this transformation did not resemble a curtain being pulled aside all at once. Light appeared first in denser regions, where halos and galaxies formed earlier. Ionized bubbles grew around individual groups of sources, taking on irregular shapes because the density of gas varied from one direction to another. A bubble could expand quickly through thin gas but slow when it encountered a dense cloud. Over time, neighboring regions touched, merged, and formed ever larger ionized zones, while pockets of neutral hydrogen remained between them. This process is commonly called reionization, because hydrogen had once existed mainly in an ionized state when the universe was extremely hot, then combined into neutral atoms as the temperature fell, and later had a large fraction of its electrons removed again by light from the first sources. The name may make the change sound like a simple repetition, but the conditions were entirely different. Ionization was no longer sustained by a uniform temperature across the whole universe, but by countless individual sources of light appearing inside halos and galaxies. Each source had a different lifetime, brightness, and environment, causing the transition to unfold over hundreds of millions of years rather than occurring everywhere at once. Stars and young galaxies are thought to have supplied most of the radiation driving this process, but the amount of ionizing light that actually escaped depended on how gas was distributed around them. A galaxy could produce many ultraviolet photons, yet if gas and dust absorbed most of them before they left the system, its effect on the intergalactic medium would remain limited. Stellar explosions could sometimes open low-density regions and channels through the gas, allowing light to travel farther. Small galaxies may have produced less light individually than larger ones, but because they were so numerous, their combined contribution may have been extremely important. Matter accreting around the first ma open subject of investigation, ma also the scale of its contribution. As the ionized bubbles merged, the space between galaxies gradually became more transparent to ultraviolet radiation. Light could travel farther before being absorbed, allowing a single source to influence increasingly vast regions of space. This, in turn, changed the formation of small systems, because ionized gas was hotter and more difficult for weakly bound halos to retain. Some small galaxies lost their fuel supply or could no longer draw in gas efficiently, while larger halos remained massive enough to hold on to matter and continue forming stars. The light produced by the earliest structures therefore did more than push back the darkness. It also helped determine which structures could keep growing and which would slowly fade. Through all these changes, gravity remained quietly present beneath every process. It gathered gas to form stars, held groups of stars inside halos, drew halos toward one another, and delivered fresh matter into young galaxies. But once stars began to shine, gravity no longer acted alone. Radiation heated the gas, explosions drove matter outward, heavy elements helped later clouds cool more efficiently, and reionization changed the conditions throughout the space between galaxies. The visible universe began to grow from the interplay between a force that always pulled matter together and sources of energy that continually moved it, scattered it, and sometimes allowed it to return. Deep within the developing cosmic web, young galaxies continued to receive gas along extended streams and to merge with neighboring systems. Some stars had already reached the ends of their lives, enriching the surrounding environment with new elements, while many others were only beginning to shine inside clouds made from matter that had already passed through several cycles of transformation. Small black holes left behind by the first stars may have continued gathering matter and slowly growing, while dark matter halos extended far beyond every luminous region visible to the eye. What had begun as scattered points of light had now become a population of interacting systems, each carrying its own history of gas, stars, radiation, and mergers. The universe was still very young, and its galaxies had not yet taken on the familiar forms they would display billions of years later. They changed constantly, sometimes brightening during an intense burst of star formation, and then fading as gas was driven away, sometimes receiving a fresh stream of matter and beginning again. There was no single moment when a galaxy could be considered complete, because from the instant of its birth, it was an open system, exchanging matter with its surroundings and responding to nearby structures. The first stars had broken the darkness, but their light had done far more than that. It created new elements, transformed the gas, expanded ionized regions, and prepared the conditions for more varied generations of stars. Within a cosmos that was slowly becoming brighter, small systems continued to move toward one another under gravity. Each time they met, stars and dark matter were rearranged, gas was compressed or driven outward, and central regions could receive new fuel. From this point on, young galaxies did more than shine. They began to consume, lose, and recycle matter, growing through streams of gas arriving from beyond, and through fragments of structures that had once followed histories of their own. Gravity continued its work, but the system it was building had become more active, more complex, and no longer understandable simply by watching matter fall inward. Young galaxies did not grow in isolation. Around them lay dark matter halos extending far beyond their luminous stars, and beyond those halos, gas continued moving along the filaments of the cosmic web. From a great distance, a galaxy might have looked like a small point of light existing alone in the darkness, but in reality, it was only the brightest part of a much larger system in which matter was continually entering, leaving, and changing state. Hydrogen atoms once scattered through intergalactic space could be drawn by gravity toward a filament of matter, flow along that filament, and then descend deep into a galaxy's halo. The journey might last hundreds of millions of years, passing through regions where the gas was so thin that each particle rarely encountered another, before the matter finally entered a denser environment and began contributing to a new generation of stars. Not all the gas entering a halo reached its central regions. As it fell deeper into the gravitational field, the gas accelerated, collided, and heated up, sometimes reaching temperatures high enough to remain as a broad halo of plasma surrounding the galaxy. Some of it could gradually cool, lose energy, and sink farther inward, while the rest continued moving along wide orbits or remained hot for long periods. In smaller halos and during certain early periods, cold streams could penetrate quite deeply without being heated completely, carrying fuel directly into regions where stars were forming. In larger halos, gas often had to follow a slower path, heating as it fell inward and then radiating away some of that energy before it could approach the galactic disk. The light of a galaxy therefore depended not only on the matter already inside it, but also on the way its larger environment continually supplied, retained, or delayed fresh gas. As gas approached the star-forming regions, its motion was rarely perfectly orderly. Streams arriving from different directions could carry different amounts of angular momentum, causing the gaseous disk to tilt, bend, or develop rings of motion that did not share the same plane. A young galaxy might receive gas from one direction for hundreds of millions of years, only for a merger or a new stream of matter to alter the entire way the system rotated. In denser regions, gas was compressed into spiral arms, bands of matter, or smaller clumps, where the temperature fell and star formation became more intense. Some of the gas became stars, while the rest continued drifting between regions, heated by radiation, pushed elsewhere by shock waves, and then cooled again. A galaxy was therefore not like a container gradually being filled. It was more like the meeting point of many currents, where matter briefly took on one form before continuing to change. The stars created from that gas did not keep their matter forever. Through most of its life, a star maintained its balance by transforming lighter elements into heavier ones within its core. As it aged, its outer layers could expand and gradually escape into space as stellar winds, or be released more violently near the end of its life. Massive stars lived briefly, emitted powerful radiation, and ended after only a tiny fraction of the lifespan of stars like the Sunday. The material they returned to their surroundings was different from the primordial gas from which they had formed, because it now contained carbon, oxygen, silicon, iron, and many other elements. Those atoms mixed into the interstellar gas, were drawn into new clouds, and could one day become part of another star, a planet, or solid matter forming around a star. This cycle was not confined to a small region. When a group of massive stars reached the ends of their lives one after another, energy from their explosions could create hot bubbles expanding through the interstellar medium. As those bubbles met, they compressed gas into dense layers along their edges, while also lifting some material high above the disk. In small galaxies, the gravitational wells were relatively shallow, so hot outflows could sometimes travel far away, carrying newly formed heavy elements with them. Some material escaped the halo entirely, but much of it reached only the outer regions, slowed down, and cooled. Over hundreds of millions of years, it could fall back into the galaxy like a very diffuse rain, carrying matter that had already passed through a generation of stars. Atoms driven outward did not necessarily reach the end of their journey. They could return, mix with fresh gas arriving from the cosmic web, and begin another cycle of star formation. In larger galaxies, this exchange unfolds across broader scales and over longer periods. The hot gaseous halo surrounding the dark matter halo can contain a substantial amount of material, yet most of it does not shine clearly in visible light. It is a reservoir that is difficult to use because the gas must lose energy before it can fall toward the central regions. Cooler clouds can condense within the hot halo, form smaller structures, and continue moving inward. At other times, energy from the center slows this process, keeping the hot gas from forming stars too quickly. The growth of a galaxy, therefore, depends on a delicate balance. Gravity tries to draw matter inward, radiation and explosions heat it or push it away, and the ability to cool determines how much of that material can return. Mergers disturb this balance in less predictable ways. As two galaxies approach one another, the gravity of each stretches the shape of the other, pulling stars and gas away from their former paths. Bright arms can be drawn into tidal tails, extending across tens of thousands of light years, while regions of gas are crowded together and strongly compressed. From a distance, a merger may appear to be two masses of stars colliding directly, but the distances between individual stars are so great that most pass through the other system without a direct collision. What changes most dramatically are their orbits. Each star begins responding to a new gravitational field that is complex and constantly shifting, disturbing the entire system before it slowly settles into a different arrangement. Gas does not pass through the encounter as easily as the stars do. Clouds of gas collide, generate shock waves, and lose some of their kinetic energy, allowing them to fall deeper toward the center of the merging system. In strongly compressed regions, star formation can increase dramatically, causing the galaxy to brighten for a relatively brief period. But that burst also quickly produces more radiation, stellar winds, and supernovae, heating the remaining gas or driving it farther away. A merger can deliver new fuel while also creating conditions that make that fuel harder to retain. After two galaxies have combined, the new system does not necessarily continue forming stars at a high rate. If most of the gas has been consumed, heated, or dispersed, the galaxy may gradually become quieter, with its light increasingly dominated by older stellar populations. Not every encounter leads to a complete merger. A small galaxy may pass through the outer region of a larger system, lose gas and stars to tidal forces, and then continue along an extended orbit. Some remain bound as satellite galaxies, circling many times and losing more material with each close passage. Stars stripped from their original systems do not disappear. They spread into long streams, so faint that they are difficult to detect without very deep observations. Stellar streams around large galaxies are remnants of smaller systems that once had histories of their own before gravity gradually dissolved them into a larger structure. The growth of a galaxy is therefore recorded not only in its bright central regions, but also in its sparse stellar halo, ancient star clusters, and subtle patterns of motion, revealing that matter once arrived from many different directions. The Milky Way carries traces of this history as well. Around its bright disk are satellite galaxies, ancient star clusters, and broad stellar streams believed to be remnants of smaller systems that have been, or are still being, stretched apart by gravity. The Milky Way's disk continues to receive gas, form stars, and exchange matter with the halo around it, while its central region contains a black hole millions of times more massive than the Sun. The galaxy's present shape is not the result of a single moment of birth, but the combined outcome of countless episodes of gas flowing inward, stars forming, matter being driven outward, and smaller systems being absorbed. Even within a galaxy that appears stable, History is still being written through motions so slow that they extend far beyond the length of any human life. At the centers of many galaxies, black holes grow together with the environments around them. A black hole does not travel throughout a galaxy swallowing everything in its path. Most stars move along stable orbits and never come close enough to fall in. The strongest effects appear when gas loses angular momentum, drifts toward the center, and forms a disk rotating around the black hole. Within that disk, matter experiences friction, heats up, and releases an enormous amount of energy before some of it crosses the event horizon. Light, winds, and sometimes narrow jets can carry energy far outward, heating gas within the galaxy or throughout the surrounding halo. This energy can slow star formation across very large scales. If hot gas cannot cool, it cannot easily contract into dense clouds. Jets from regions near a black hole can carve vast cavities into the hot gas of a galaxy cluster, transporting energy tens or even hundreds of thousands of light-years from the center. Although a black hole contains only a very small fraction of a galaxy's total mass, the process of matter falling into it can influence how much gas remains available to form stars. In some cases, pressure from these outflows can compress gas in certain regions and temporarily encourage star formation. But over long periods, the effect usually acts as a form of regulation, preventing gas from cooling and turning into stars too quickly. This regulation is especially important for explaining why galaxies do not convert all their gas into stars within a short time. If gravity alone continually drew gas inward, without radiation, supernovae, or black hole activity returning energy to the environment, many models would produce star formation far more efficiently than observations suggest. The real universe retains a large amount of ordinary matter outside stars, within interstellar gas, hot halos, and the medium between galaxies. Some fuel always remains in a state that cannot yet be used. Some is driven outward and later returns, while some may never come back to the galaxy that released it. The starlight we observe therefore represents only a small fraction of all the matter that has passed through these systems. Over time, each galaxy develops a rhythm of its own. Some continue receiving abundant cold gas, sustaining star-forming regions, and preserving the blue light of young stellar populations. Others enter galaxy clusters, where hot gas and rapid motion reduce the supply of new material or strip gas away from the galaxy. As the remaining fuel is gradually exhausted, star formation slows, and the galaxy's light becomes increasingly dominated by older stars. A galaxy may remain quiet for a time, and then become active again if it receives fresh gas or merges with a fuel-rich system. These states are not necessarily permanent endpoints, but phases within a long history in which environment and interaction continue to reshape the conditions inside. From far enough away, all of these processes disappear into a single point of light. We cannot see each cloud of gas cooling, each explosion driving matter outward, or each atom that has left the disk and is slowly returning. Yet these nearly invisible motions determine the brightness, color, shape, and rate of star formation of the entire galaxy. A system grows not simply by retaining everything it encounters, but through a kind of selection governed by gravity and energy. Some matter is kept, some is lost, and some leaves for a time before returning after a long journey. As millions of galaxies pass through these cycles, their light begins to reveal the larger shape of the universe. Regions that receive more matter produce more halos and more galaxies, while thinner regions gradually lose gas into streams flowing toward denser areas. Galaxies are not scattered evenly through space because their supplies of fuel and their gravitational histories are not distributed evenly either. They appear in groups, extend along enormous filaments, and gather where many streams of matter meet. Each galaxy carries its own story of what it has received, lost, and recycled, but its position belongs to a much larger story, written on scales far greater than any individual stellar disk or halo. There, the streams of gas-feeding galaxies no longer appear as separate flows, but as parts of vast filaments of matter connecting dense regions across space. Galaxy clusters form at the intersections, while between them lie voids that continue to expand. Gravity created stars and gathered them into galaxies, but the deepest shape of that construction only becomes visible when the view pulls back far enough for every galaxy to become a small point within an immense network. When the perspective recedes until a galaxy is reduced to a tiny point of light, the distribution of matter begins to reveal a different form. The luminous points are not scattered evenly like dust across a sheet of glass, nor do they arrange themselves in balanced circles around a single center. They gather into long bands, broad walls, and dense knots, while enormous dark regions open between them, where galaxies are far less numerous. On this scale, the universe resembles a network so vast that light takes hundreds of millions of years to travel from one end of some structures to the other. Every galaxy still has a history of its own, but its location is not entirely random. It lies where streams of matter have flowed for billions of years, where gravity once drew material away from thinner regions and toward places of greater density. The shape of this network did not emerge because matter was pulled evenly into separate spheres. The original irregularities in the universe were not so round or symmetrical. A region could be compressed more strongly in one direction, while remaining extended in others. As gravity drew matter together, collapse often proceeded unevenly. Matter might first gather into a thinner layer, like a broad sheet stretching through space. That sheet could then contract along another direction and form a longer filament. Where several filaments met, the density rose sharply, creating large knots where galaxy clusters could develop. No one drew these connecting lines in advance, and no single pattern was repeated everywhere. The structure arose from the way gravity amplified tiny initial irregularities along different directions. From inside a galaxy, this network is almost impossible to sense directly. The distances to other galaxies are too great, and the filaments themselves are too broad for an observer to recognize that they are located within an extended structure. Only when millions of galaxies are placed on the same map do the curves and concentrations begin to emerge. Bright galaxies serve as markers across a landscape that is mostly invisible. They reveal where matter has gathered long enough to form stars, but they do not contain all the mass of the network. Most of the structure is still held together by dark matter, while the gas between galaxies is often too thin, too hot, or too faint to observe easily. A cosmic filament, then, is not simply a chain of galaxies lying near one another. The points of light reveal only a small part of a much broader flow of matter. Between the galaxies may lie gas extending across millions of light years, spread so thinly that individual particles are separated by enormous distances. Some of this gas is hot enough to emit faint X-rays. Other portions exist at intermediate temperatures and can be detected only through tiny absorption signatures imprinted on light from background sources. Dark matter provides most of the mass and shapes the shared gravitational field, while galaxies are only local regions where gas has collapsed deeply enough to form stars. Seen in this way, galaxies are like lamps placed along a road at night. Their light reveals the direction of the road, but the road itself is not made from the lamps. Matter within the filaments does not remain still. Gas and small halos continue moving along the length of the structure, slowly drifting toward regions of greater density. A galaxy may receive gas from its surroundings, while its entire halo moves with a larger gravitational flow. Small galaxies can be drawn into groups, groups can move toward clusters, and clusters can form where several filaments intersect. This process does not resemble a river flowing across the ground with clear banks and a fixed direction. The paths curve, streams overlap, and some matter passes through central regions before continuing outward. Even so, the overall tendency remains the same. Places that already contain more matter continue receiving more, while regions with less matter gradually become thinner. The spaces between filaments are often called cosmic voids, but the name can suggest regions that are completely empty. In reality, they still contain dark matter, gas, and some galaxies, only at densities below the cosmic average. Small galaxies can live in near isolation within them, developing more slowly because they receive less gas and experience fewer interactions. On large scales, however, matter in the voids tends to move outward toward the surrounding walls and filaments. As denser regions draw in more material, the voids lose some of their mass and become more pronounced. Because space continues to expand, low-density regions can grow faster than places more strongly held together by gravity, causing them to occupy an increasing fraction of the universe's volume. A single void can be so wide that light takes tens or hundreds of millions of years to cross it. From within, it would not necessarily appear as a completely black abyss because scattered galaxies would still be present and the sky would still contain light from more distant structures. Its emptiness becomes clear only when the density of galaxies is compared across a very large region. These voids are not leftover spaces between the important structures. They are the other half of the same process. Each time matter flows out of a thin region toward a denser one, a filament or knot becomes more distinct, while the void itself grows deeper. The cosmic web is shaped not only by where matter gathers, but also by where matter has departed. At the great intersections of filaments, galaxy clusters form as the densest knots in the network. A cluster can contain hundreds or thousands of galaxies, all moving within an enormous shared gravitational field. Yet if we add together only the light from their stars, most of the cluster's mass is still missing. The luminous galaxies make up only a small portion, while dark matter supplies most of the gravity holding the entire system together. Between the galaxies lies a vast amount of gas heated to tens of millions of degrees, glowing in X-rays rather than visible light. In many clusters, more ordinary matter exists in this hot gas than in all the stars combined. From a distance, a galaxy cluster may appear to be a peaceful collection of points of light, but within it are motions unfolding over billions of years. Galaxies race through the hot surrounding gas at high speeds, losing some of their own gas and gradually becoming less able to form stars. Small galaxy groups fall into the cluster, changing the distribution of mass and generating shock waves in the gas. Two clusters may approach, pass through one another, and slowly merge into a larger system. When this happens, dark matter and galaxies mostly pass through with few direct collisions, while the hot gas is compressed, slowed, and left behind in extended regions of X-ray emission. On human timescales, the cluster seems unchanged. On cosmic timescales, it is still a structure in the process of forming. Gravity binds clusters together, but not every larger collection is a single object that can remain intact forever. Several nearby clusters can form regions often called superclusters, extending across immense distances. The name may make them sound like larger versions of galaxy clusters, but their boundaries are not so simple. A cluster is usually a tightly bound system whose members move within the same gravitational well. A supercluster can contain many clusters and galaxy groups occupying the same overdense region, but not every part is held strongly enough to eventually merge. Across very large distances, the expansion of space continues, and some regions may drift farther apart even though they belong to the same named structure on a map. Great size, then, does not automatically mean lasting gravitational unity. A structure may be easy to recognize visually or statistically, yet its future depends on whether gravity is strong enough to overcome the tendency of space to expand. Dense central regions may continue collapsing and merging, while the outermost parts are gradually drawn away. This means the cosmic web is not a rigid net stretched permanently across space. It is a changing field of matter in which some knots grow tighter, some filaments are stretched, and the voids continue to expand. This structure can be recreated in simulations by beginning with an almost uniform universe, adding density fluctuations consistent with the cosmic microwave background, and then allowing gravity to act for billions of years. At first, the differences are only gentle ripples. Over time, dark matter gathers into halos, halos connect into filaments, and regions with less matter become voids. When gas is added, along with cooling, star formation, and energetic feedback. Galaxies appear wherever the network has created gravitational wells deep enough to support them. There is no need to place each galaxy into position by hand. They emerge naturally, wherever the history of the density field allows them to form. The similarity between simulations and observational maps is one of the reasons the modern picture of structure formation is considered so compelling. Even so, resemblance does not mean that every detail has been resolved. The way gas flows into halos, the strength of feedback from stars and black holes, the distribution of small galaxies, and the internal structure of cosmic voids can all vary from one model to another. Dark matter reveals its role through gravity, but the nature of the particles that make it up remains unknown. Small differences between observations and simulations may arise from extremely complex gas processes, from the limits of measurement, or from some part of physics that has not yet been described completely. When we look at a map of the cosmic web, the bright filaments often make the strongest impression, but much of the structure's true depth lies in what cannot be seen directly. A galaxy shines because gas has cooled, contracted, and formed stars, while the dark matter around it remains invisible even as it governs the orbits within. Gas between galaxies may contain a significant fraction of ordinary matter, yet leave behind only a faint signal. Voids appear almost empty, but they still preserve evidence of how matter was drawn away from them. Every part of the network is therefore a layer of history, recording the directions matter traveled, the places where it came to rest, and the regions where it never gathered deeply enough to create many sources of light. The Milky Way lies within this structure as well. It belongs to a small group of galaxies that includes Andromeda and many dwarf galaxies, and this group exists within a broader region connected to nearby clusters and filaments. From inside the solar system, we see only a luminous band of stars crossing the night sky, but the position of the Milky Way was shaped by flows of matter on far greater scales. Gas once traveled through filaments, small halos once merged, and satellite galaxies were drawn inward, all carrying the imprint of the same process that began when the universe was still nearly uniform. If we continue pulling farther back, individual galaxies gradually disappear from view. Clusters become small bright knots, and filaments turn into thin lines stretching across the darkness. On sufficiently large scales, the structure no longer resembles a collection of separate objects, but a continuous field in which density rises and falls across vast regions. Gravity transformed the original variations into a landscape with depth, allowing matter to flow downhill in a gravitational sense, leaving voids behind and adding mass to knots that grew steadily heavier. But this work did not unfold in a motionless universe. While gravity drew matter together, the space between distant regions continued to expand. In the early universe, matter was denser, giving gravity more opportunity to amplify small differences. Later, as the universe became more diffuse, the growth of new structures slowed. Clusters that were already bound could continue holding their members, galaxies could still merge, and gas could still fall into existing halos. But on the very largest scales, the cosmic web could not continue thickening forever at the same pace. The knots, filaments, and voids visible today therefore reveal not only what gravity has accomplished, but also how much time it has had to do so. Every structure is the result of a contest lasting billions of years between gravitational collapse and cosmic expansion. Gravity deepens dense regions, while expanding space increases the distance between places too far apart to strongly influence one another. The cosmic web exists between these two tendencies, neither collapsing into a single mass nor stretching back into a perfectly uniform distribution of matter. From tiny fluctuations in the primordial glow, matter has traveled a long path to become halos, galaxies, filaments, and clusters. Regions that were once only slightly denser than their surroundings now contain thousands of galaxies, while places that were once slightly thinner have become voids so vast that light takes an almost unimaginable length of time to cross them. The deepest shape of the universe is not contained within any single star or galaxy, but in the way all these objects are arranged together across a network that continues to change. As light from distant galaxies passes through this network on its way to us, it carries more than an image of the sources that emitted it. Its path is bent by intervening matter. Its wavelengths are stretched by expansion, and the distribution of billions of galaxies preserves clues to the rate at which structure once grew. The cosmic web itself has become a record, with the history of gravity stored in the positions, shapes, and separations of luminous objects across the sky. Gravity created knots and filaments by drawing matter toward the smallest initial differences, but expansion continues to enlarge the space between distant structures. From here, the question is no longer only how the cosmic web formed, but how much farther it can continue to grow as the force pulling matter together exists within a universe whose expansion is accelerating. Across the immense map of the universe, filaments of matter still connect galaxy clusters, while voids continue to widen between dense regions. Looking at this structure, it might seem that gravity is slowly winning everywhere because matter has left its nearly uniform state and gathered into stars, galaxies, and enormous knots within the cosmic web. Yet throughout the entire time gravity was drawing matter inward, another process never stopped. The space between sufficiently distant regions continued to expand, carrying unbound structures farther apart. The cosmic web therefore records not only where matter has gathered, but also the traces of a balance lasting billions of years between the tendency to concentrate matter and the tendency to increase the distances between it. Cosmic expansion is not like a wind blowing galaxies through a stationary space, nor is it the fading aftermath of an explosion from one central point that hurled matter outward. Across very large distances, the scale of space itself changes over time, allowing the distance between regions that are not gravitationally bound to increase even while each galaxy remains almost at rest within its local environment. There is no single center from which all galaxies are flying away, because an observer in any galaxy would see sufficiently distant systems receding according to the same overall pattern. Light must cross this changing space, and as it travels, its wavelength is stretched, carrying evidence of how much the universe has expanded since the photon began its journey. Expansion, however, does not act in the same way on every scale. The moon is not pulled away from Earth, stars are not separated from their galaxies, and galaxies already deep inside a cluster do not simply drift apart because the wider universe is expanding. In systems like these, gravity or other forces are strong enough to preserve the bond. The distance between Earth and the Sun is determined mainly by Earth's orbit within the Sun's gravitational field, not by the growing separation between distant galaxy clusters. Even Andromeda, despite the expansion of the universe, is moving toward the Milky Way because gravity within the local group is stronger than the tendency of expansion across the relatively small distance between the two galaxies. Only when we look far enough beyond regions that are already gravitationally bound does expansion become the dominant motion shaping the overall picture. When the universe was still young, the density of matter was far greater than it is today. Dense regions lay closer together, and each volume of space contained more material, giving gravity more opportunity to amplify the original variations. A region only slightly heavier than its surroundings could slow its own local expansion, retain more matter, and gradually separate from the general outward flow. Gas and dark matter continued falling inward, halos grew, and lower density regions slowly lost material to the filaments and knots. While the universe as a whole kept expanding, many smaller regions could still contract. Two motions that seemed to oppose one another existed at the same time. The distances between very remote regions increased, while within areas dense enough, matter moved ever closer together. Imagine a galaxy cluster forming within an immense expanse of space. Nearby galaxies fall toward the center. Gas is heated as it enters the gravitational field. Smaller groups merge, and the mass of the cluster gradually increases. Farther outside, regions that do not belong to that gravitational well continue to follow the general expansion. The boundary between these two domains is not a fixed wall, but depends on mass, distance, and the motion of matter. A galaxy close enough may be captured and eventually join the cluster. A more distant galaxy may never arrive because the space between them continues to expand. Over time, gravity determines what can become part of a shared system, while expansion places a limit on how far that system can continue gathering material. For much of the universe's early history, it was reasonable to expect the pull of all its matter to gradually slow the expansion. Matter would not stop the universe from expanding immediately, but its gravity would resist that motion, much as an object thrown upward continues to rise while slowing under Earth's pull. If the universe contained only radiation, ordinary matter, and dark matter, its expansion history would be determined by the amount of matter present and the geometry of space. Galaxy clusters would continue to form, the cosmic web would grow more pronounced, and the expansion rate would tend to decline over time. For a long while, the observed picture seemed consistent with this intuition, because there was no obvious reason why a universe filled with matter should suddenly begin expanding more rapidly. Near the end of the 20th century, light from very distant stellar explosions told a different story. Type Ia supernovae can be used to compare observed brightness with distance, and when their light was measured across different redshifts, the history of expansion did not match the prediction for a universe that was only slowing down. During the last several billion years, the expansion has shifted into an accelerating phase. Unbound regions have not merely continued moving apart. The rate at which their separation increases because of expansion has itself grown over time. This discovery did not suggest that galaxies had suddenly received a push through space, but that the expansion of space itself had changed the way it developed. The name dark energy was given to the component or effect thought to lie behind this acceleration, but the name does not explain its nature. In the standard cosmological model, the simplest description is a form of energy associated with space itself, usually represented by the cosmological constant. As space expands, the density of matter falls because the same amount of matter is spread through a larger volume, while the density associated with the cosmological constant does not decline in the same way. Early on, when matter was still dense, the influence of this component was too small to dominate the evolution of the universe. Later, matter became more diffuse while the energy associated with space remained, and the balance gradually shifted. A component that had once been almost negligible began to determine how the largest distances evolved. Dark energy is not a dark substance moving through galaxies, nor is it the same as dark matter, even though the two names often appear together. Dark matter adds gravitational pull, helps hold galaxies and galaxy clusters together, and supports the growth of early structures. Dark energy is used to describe an effect acting in the opposite direction on cosmic scales, accelerating expansion and making it increasingly difficult for very distant regions to exchange matter. One component helped build the framework of the cosmic web, while the other gradually limits how much that web can continue growing across the greatest distances. They are not two well understood aspects of the same thing, but two separate questions revealed through very different effects. As accelerated expansion became important, gravity within bound systems did not disappear. Stars continued orbiting galactic centers, satellite galaxies could still fall into larger systems, and members of galaxy clusters continued interacting. The Milky Way and Andromeda still moved toward one another. Galaxy clusters could still merge, and gas continued falling into halos that had already formed. In the simplest form of the current model, dark energy is not strong enough to tear apart atoms, planetary systems, or galaxies. The change is more subtle. Matter lying beyond already bound regions becomes increasingly difficult to draw inward because the distance between it and the dense structure continues to grow at an ever faster rate. A galaxy cluster can continue rearranging what already lies within its gravitational reach, but its ability to attract matter from extremely distant regions gradually becomes limited. Cosmic filaments do not cease to exist, yet the flow of matter through them cannot continue increasing forever at the same pace it did in the young universe. Regions that are already dense can still become denser, while voids expand and occupy an increasing fraction of the total volume. The network continues to change, but its overall growth slows. Gravity's work has not ended, yet the material available to it is gradually being divided into regions that grow more and more isolated. This helps explain how the modern universe can contain violent events while also undergoing a large-scale slowdown in structure growth. Two galaxies can collide, gas can be compressed, and billions of new stars can form within a merging system, while regions billions of light-years away are still being carried farther apart by expansion. Intense activity in one location does not mean the entire cosmic web is growing more rapidly. Gravity continues working within local regions, rearranging matter that was gathered earlier, while the overall evolution of the universe makes it increasingly difficult to create new bound structures on the very largest scales. If acceleration continues as the current model predicts, the distant future will bring ever greater isolation between bound regions. Galaxies within the same group may merge and form a single large system, while clusters beyond them recede farther away. Light emitted by those distant structures must cross space that is expanding more rapidly, becoming stretched to longer wavelengths and growing fainter before it arrives. Over immense periods of time, many structures visible today may pass beyond the observable reach of anyone living in a future galaxy, not because those structures have vanished, but because the distance between regions increases so quickly that new signals can no longer reach them. The network that once connected bright knots across the cosmic map will gradually be divided into isolated gravitational islands. Yet that future depends on what dark energy truly is. If it corresponds exactly to a cosmological constant, its density will remain unchanged and the acceleration will follow a relatively steady course. If dark energy changes over time, the future history could be different. It might weaken, grow stronger, or reflect an unknown physical field. It is also possible that what we call dark energy is not a new component at all, but a sign that our present understanding of gravity must be modified when applied across the largest distances. Current measurements agree quite well with the simpler model, but they are not enough to turn the nature of cosmic acceleration into a question that has been fully settled. One way to search for what is missing is to compare two histories recorded within the same universe. The first is written in the distances and redshifts of galaxies, revealing how space has expanded over time. The second is written in the degree to which matter has clustered, showing how quickly density fluctuations have grown. If dark energy changes only the expansion of the universe within the framework of general relativity, then the rate of structure formation should follow a particular relationship with the expansion history. If gravity behaves differently on the largest scales, those two histories may no longer match in the same way. The difference is extremely subtle and cannot be recognized by looking at a single galaxy. A galaxy may be large or small because of its own merger history, the amount of gas it has received, or the activity of the black hole at its center. To separate cosmological effects from local variations, scientists must observe enormous numbers of galaxies across broad regions of the sky, measure how they cluster at different times, and search for the tiny distortions that intervening matter leaves on light from more distant sources. The farther we look, the earlier the era from which the light has traveled, allowing different layers of the cosmic web to be placed beside one another like surviving pages from a history spanning billions of years. On one very ancient page, galaxies are still young, clusters remain incomplete, and matter is gathering rapidly. On pages closer to the present, the knots have grown, the voids have widened, and the growth of structure has begun to slow. No telescope can watch the entire process unfold in one place from beginning to end, but the sky preserves many different moments in light arriving from different distances. By assembling those moments, We can follow the competition between gravity and expansion, not as two forces confronting each other along a clear boundary, but as two tendencies shaping the entire history of cosmic structure. The cosmic web today lies between two regions of time. Behind it is an era when matter was denser, fluctuations grew more rapidly, and halos merged continuously. Ahead lies a future in which bound systems will continue to change, while distant regions become increasingly unable to reach one another. The filaments, clusters, and voids across the sky are not only forms created by gravity, they also preserve the imprint of the time when expansion began to slow that construction. Light from billions of galaxies travels through this structure before reaching us. Along the way, it is stretched by expansion, bent by dark matter, and carries images of galaxies at many different stages of development. Every photon is a tiny piece of the record, while the entire sky forms an immense archive of how gravity once gathered matter and how space gradually limited the reach of that gathering. To read this record, we must observe not only what shines, but also the nearly invisible distortions between the sources of light, where unseen mass still leaves its mark on the paths those photons have followed. In a universe whose expansion is accelerating, gravity has not stopped building. It continues to draw gas into galaxies, bring smaller galaxies toward larger systems, and keep enormous clusters from dissolving into the surrounding space. But on the largest scales, that construction has already passed through its most vigorous period of growth. The remaining material is becoming more widely separated, while the structures already built are slowly turning into distinct regions within expanding space. What remains uncertain is whether this change follows the known laws of gravity completely, and what component is causing the expansion rate to increase after billions of years of slowing down. The answer is not contained in any single galaxy, individual stellar explosion, or prominent cluster. It is spread very thinly across the sky, in the positions of billions of galaxies, in their subtly altered shapes, and in distances that have changed over time. To understand how much gravity managed to build before expansion began slowing the process, we must turn the deep universe into a map, broad enough to reveal the cosmic web and precise enough to detect the faint traces left by invisible matter. Light from a distant galaxy does not reach us at the moment it is emitted. It must cross immense stretches of space, travel alongside the filaments of the cosmic web, pass through thin regions of gas and invisible dark matter halos, while space itself continues expanding along the way. Some photons began their journey before Earth formed, before the Sun appeared, and before the Milky Way had taken on anything close to its present shape. When that light is finally recorded by a telescope, it brings not only an image of a very distant galaxy, but also a slice of the universe as it existed in the past. Looking deeper into space is therefore also looking farther back in time, as though the sky had preserved many different ages upon the same dark background. No observatory can leave the universe and view the entire cosmic web from the outside, nor can it wait billions of years to watch a galaxy cluster grow from beginning to end. Instead, light arriving from different distances allows an indirect history to be assembled. Nearby galaxies appear at relatively late stages, while more distant galaxies are seen when they were younger, at a time when clusters were still incomplete and matter was gathering more rapidly. With enough observations, these slices can be placed beside one another, not to follow a single galaxy through every stage, but to reveal how the entire population changed over billions of years. Euclid was sent into space to carry out this kind of observation on an unprecedented scale. From a stable location about 1.5 million kilometers from Earth, the telescope slowly surveys selected regions of the sky, recording galaxy light with two instruments operating in visible and near-infrared wavelengths. Over several years, individual patches of sky will gradually be joined into a map covering more than 1/3 of the celestial sphere, containing billions of galaxies across roughly 10 billion years of cosmic history. Each galaxy occupies only a tiny part of an image, sometimes no more than a faint streak of light. But when billions of those streaks are measured by the same system, they can reveal patterns that would remain invisible in any single object. For many distant galaxies, what matters is not only brightness or color, but shape. A galaxy may naturally be round, flattened, elongated, or distorted because of its own history. The light it emits continues across the universe and encounters regions of mass along the way. According to general relativity, mass changes the geometry of spacetime, bending the path of light. When the intervening matter is dense enough, the effect can stretch background images into prominent arcs or create several images of the same source. But most of the cosmic web does not produce distortions that are so easy to see. It alters the apparent shape or orientation of a galaxy by only an extremely small amount, usually too slight to distinguish from the galaxy's natural form. A single galaxy cannot clearly reveal how much its light has been altered, because no one can see its original shape before the photons pass through the layers of matter in front of it. But galaxies lying near one another on the sky have no reason to share a particular orientation simply because of their natural forms. If many distant galaxies show a small but correlated pattern of distortion, that similarity may come from the common gravitational field through which their light has traveled. As the number of sources grows from millions to billions, the noise created by the individual shapes of galaxies is gradually reduced through statistics, leaving behind a faint but structured signal. From that signal, the distribution of intervening mass can be inferred. Regions that bend light more strongly generally contain more matter, even when most of that matter emits no light of its own. The resulting map is not a direct photograph of dark matter. The telescope does not capture dark matter particles, nor does it see any color or surface belonging to them. Instead, dark matter appears through the accumulated influence its mass leaves on the paths of light. Billions of distant galaxies become background sources, and their tiny apparent shapes act like delicate needles, responding together to an invisible gravitational landscape spread across space. That landscape has depth as well as width across the sky. Light from galaxies at different distances has passed through different portions of the cosmic web's history. When the sources are divided, according to the eras in which they existed, the layers of matter in front of them can also be studied at different depths. A dense region, seen at an early time, can be compared statistically with structures at later times, revealing how much density fluctuations have grown under gravity. Each individual layer remains faint and noisy, but when the layers are combined across a vast region of sky, a three-dimensional map of matter begins to emerge, not as a fixed sculpture, but as many states of the same cosmic web unfolding through time. Euclid also reads this history through the positions of the galaxies themselves. They are not scattered randomly through space, but tend to appear close together in dense regions, connecting into filaments and gathering around large clusters. The degree of clustering changes over time because gravity continues to amplify the differences. Slightly denser regions receive more matter, while thinner regions gradually lose material to nearby structures. By measuring the distances between countless galaxies and how their distribution changes from one era to another, scientists can trace how quickly the cosmic web became more distinct, how its knots grew, and when the growth of structure began to slow. Hidden within that distribution is an ancient distance scale. When the universe was still a hot plasma, gravity drew matter toward denser regions, while radiation pressure pushed the mixture of matter and light outward, creating waves that traveled through the primordial medium. When atoms formed and photons separated from matter, those waves stopped propagating in the same way, leaving behind a slight preference in the probability of finding matter at a particular distance from an initial region. After billions of years of expansion, this imprint has been stretched into an enormous scale between galaxies. It does not appear as a clear circle surrounding each galaxy, but when millions of pairs of sources are measured, a very small excess in their distribution can be detected. This distance scale is often treated as a kind of standard ruler left behind by the early universe. Its original size can be inferred from the physics of the plasma and from the cosmic microwave background. By observing the apparent size of the imprint at different eras, scientists can test how space expanded while the light was traveling toward us. If a ruler of known length appears smaller or larger in a particular way, the difference reveals how the distances between galaxies have changed. No solid object has been placed in space as a measuring device. There is only a statistical memory left behind by waves that crossed the universe before the first star was born. The distorted shapes of galaxies and the way galaxies cluster tell two different parts of the same history. Weak gravitational lensing is sensitive to the total amount of matter along the path of light, including the dark component that emits no light. Clustering shows how galaxies are arranged within that field of matter and provides information about distance and the rate of expansion. When these two measurements are considered together, ambiguities that are difficult to resolve with one method can be clarified by the other. A universe containing more matter may produce stronger structure. A different expansion history may alter the observed distances. A different form of gravity may cause the rate of clustering to no longer agree with the degree of expansion. Combining these traces allows scientists to test whether all parts of the picture are telling the same story. This is also where the competition between gravity and expansion can be measured rather than merely imagined. The distances and redshifts of galaxies reveal how the universe has expanded over time, while lensing and clustering reveal how quickly matter has gathered. Under general relativity, with a given amount of dark matter and dark energy, these two histories must be related in a way that can be calculated. If accelerated expansion is caused by a constant associated with space, the growth of the cosmic web should follow a particular path. If dark energy changes over time, or if gravity behaves slightly differently across billions of light years, structure may grow faster or slower than predicted. No single gas, its individual history is too complex, shaped by the amount of gas it receives, its mergers, stellar radiation, and the activity of the black hole. The cosmological signal appears only when those individual features are averaged across enormous populations. This is why Euclid requires such a wide survey and such a vast number of galaxies. Every individual measurement is imperfect, but billions of weak measurements can combine into a powerful constraint, much like a whisper that is almost impossible to hear becoming clearer when it is repeated in the same rhythm across the entire sky. That level of precision also makes small biases in the instruments or data important. The image of a galaxy can be affected by the motion of the telescope, its optics, the detector, and the way the light is processed after being transmitted to Earth. Earth's atmosphere does not lie along Euclid's line of sight, but the instrument itself still leaves signatures that must be carefully measured and corrected. Distances to remote galaxies are often inferred from their colors or spectral lines, and each method carries its own uncertainties. Galaxies whose natural shapes are correlated with their environments can also produce signals that resemble part of the weak lensing effect. To detect the extremely subtle influence of dark energy or a deviation in gravity, closer and more familiar effects must be understood with comparable precision. A wide map, therefore, does not automatically become an answer. The data must be calibrated, compared, and tested against other surveys. The same regions of sky can be observed at different wavelengths to determine colors and distances more accurately. Simulations are used to test whether the processing might accidentally erase a real signal or create a pattern that does not exist. Independent teams can analyze the same trace with different methods, checking whether the result remains stable when the criteria for selecting galaxies or the modeling of secondary effects are changed. This slow work attracts less attention than colorful images of nebulae and galaxies, but it is what determines whether a tiny distortion in the sky truly belongs to the structure of the universe or comes only from the way humans measure light. Euclid does not begin the story at its first page. The initial conditions have been measured most clearly through the cosmic microwave background, especially in the all-sky maps produced by Planck. Within the light released when the universe was about 380,000 years old, Planck recorded extremely small temperature fluctuations related to the original differences in density. Those traces are like an image of seeds before any forest had appeared. Euclid looks at the later part of the history, when those seeds had become halos, filaments, galaxies, and clusters, and measures how they developed across many different eras. Placing the two ends of the history side by side creates a special test. From the cosmic microwave background, scientists can estimate the initial state of the fluctuations and the amount of matter required by the model. The laws of gravity can then be used to predict how those fluctuations should grow into structure. If maps of galaxies and dark matter from later eras agree with those predictions, the story from the early universe to the modern cosmic web becomes more consistent. If the observed growth differs systematically from what was expected, the missing piece may lie in the nature of dark energy, the properties of dark matter, the mass of neutrinos, the way gravity operates, or some assumption that was once considered sufficiently accurate. Even if Euclid creates a map with unprecedented detail, dark matter may still not reveal the type of particle from which it is made. A gravitational map shows where dark matter is located and how it influences structure on large scales, but it may not distinguish between every microscopic possibility. Dark energy may also continue to agree with a simple constant without explaining why that constant exists or why it has the value we observe. A result consistent with the current model does not turn the unknown into the known. It only narrows the space available for other possibilities. Conversely, even a small deviation would need to be examined for a long time before it could be regarded as evidence of new physics. According to ESA's current release schedule, Euclid Data Release 1 is expected on the 21st of October 2026. That release will not be the final image of the entire survey, because Euclid will still need several more years to complete its broad region of sky and accumulate the required depth. It will be more like the first substantial page of a map still being assembled, where millions of individual sources begin to be organized into datasets that can be explored in many different ways. Major cosmological conclusions will require time, the combination of multiple data releases, and far more careful control of uncertainties than simply counting the number of galaxies appearing in an image. When all of this work is reduced to a simple image, Euclid can be imagined as a telescope looking at light while searching for things that mostly do not shine. It measures the shapes of galaxies to infer the matter between them, measures their positions to reveal the surrounding network, measures their colors and spectra to place the sources within the depth of cosmic time, and then compares the growth of structure with the way space has expanded. Photons arriving from far away have been stretched, bent, and sometimes absorbed during their journey, but those very changes transform them into messengers from the parts of the universe that cannot be seen directly. From a small observing point near Earth, the map gradually extends across billions of light years. Individual galaxies become markers along filaments. The filaments meet at enormous clusters. Weak lensing reveals layers of dark mass surrounding and lying between them. Every distance corresponds to a different era, allowing the cosmic web to appear not only across space, but also through its evolution. In the more distant layers, the structure is still young and the fluctuations have not yet grown deeply. In the nearer layers, the knots are denser, the voids are wider, and the influence of accelerated expansion has become more apparent. The sky becomes a long cross-section through the history of gravity, recorded not in words, but in the positions and shapes of light. Long before Euclid began surveying the sky, tiny fluctuations in the primordial plasma had already left their imprint on the cosmic microwave background. Much later, gravity amplified those same fluctuations into wells of dark matter, drawing gas inward, creating stars, and connecting galaxies into a vast network. Now, light from those galaxies is bent by that very network before it reaches the telescope. Cause and evidence almost complete a circle. Gravity builds structure, structure alters light, and light tells the story of how gravity has worked. The final map may show that the current model describes the universe more accurately than we ever hoped. Or, hidden among countless tiny measurements, a persistent mismatch may appear, suggesting that the growth of structure does not completely agree with the history of cosmic expansion. Whatever direction the results take, the record being read begins from the same origin, a universe that was almost uniform, but not perfectly smooth, where some regions contained only slightly more matter than their surroundings. Those differences were once too weak to create any visible form. Over time, they became dark halos, clouds of gas, the first stars, galaxies, clusters, and filaments of matter stretching across space. Once the network had grown large enough to surround billions of sources of light, human beings began using that same light to trace gravity's work backward. A telescope cannot step outside the universe and view the entire construction at once, but by listening to billions of faint signals together, it can gradually recognize the outlines that time has left behind. In the night sky, every distant galaxy still appears as little more than a small, quiet, nearly motionless streak of light. Behind that stillness lies a history spanning billions of years, during which matter flowed out of voids, gathered along filaments, and fell into dense knots, while space continued expanding between regions too distant to hold one another. Euclid does not see gravity as an object, but it can read where gravity has passed, how it has arranged matter, and where expansion began slowing the growth of structure. From the ripples in the universe's earliest light to the extremely subtle distortions and images of distant galaxies, the cosmos has preserved both ends of the same story. At one end are seeds that were almost invisible. At the other is an immense network now passing through a slower period of growth. Between them lie billions of years during which gravity quietly pulled matter toward matter, not according to a predetermined design, but by following tiny differences that had existed since before the universe contained any source of light. As the view continues to pull away from the galaxies Euclid is recording, individual details gradually disappear. Spiral arms can no longer be distinguished. Light from star-forming regions blends into the rest of each galaxy, and even enormous clusters shrink into bright knots along thin filaments of matter. Farther still, the knots and filaments themselves begin to dissolve into a broad layer of structure, where no single object remains distinct enough to hold our full attention. All that remains are dense regions connected to one another, expanding voids between them, and a network extending across distances far beyond anything a human life can directly experience. Within that structure, the history of gravity is still present. It lives in the orbits of stars around galactic centers, in the motion of galaxies within clusters, and in the way gas has flowed from sparse regions toward filaments for billions of years. It is also present where little light can be seen, within dark matter halos, extending far beyond visible stars, and within voids from which matter has gradually departed. Gravity did not choose a special place to begin its work, nor did it hold an advance image of the structures it would create. It simply responded to the distribution of matter at every moment, pulling more strongly where more matter was already present and allowing time to amplify differences that had once been extremely small. Stars emerged from gas falling into gravitational wells, but the stars themselves then changed the gas. They produced light, heated their surroundings, created new elements, and returned part of their material to space. Galaxies grew through streams of gas arriving from the cosmic web, but they also lost gas through radiation, stellar winds, supernovae, and the activity of black holes at their centers. Galaxy clusters gathered thousands of systems within a shared gravitational field, while the space between clusters continued expanding. The construction of the universe was therefore never a simple process of building one layer after another in a single direction. Matter gathered and dispersed, heated and cooled, left galaxies, and sometimes returned hundreds of millions of years later. The form visible today is only the temporary result of all these motions existing together. If we trace every step backward, clusters become smaller groups, galaxies return to gas and merging halos, and the first stars become hot hydrogen cores hidden in darkness. Before those cores came primordial clouds that could contract only after releasing enough heat. Before the clouds came dark matter wells that emitted no light. And before even those gravitational wells, there was a hot, luminous, nearly uniform universe in which every future structure existed only as a difference in density so small that no star or galaxy could yet be seen within it. At that time, there was no clear sign that one region would become a galaxy cluster, while another would expand into a void. No lines indicated which way gas would flow, and no location had been marked for the future Milky Way. The first ripples were only faint possibilities within the distribution of matter and energy. But gravity has a remarkable property. It does not require a difference to be large at the beginning. If one region contains only a little more matter than its surroundings, its gravitational pull is also a little stronger. As long as that advantage is not erased, time can transform an almost invisible variation into a structure large enough to contain trillions of stars. Had the early universe been perfectly uniform, no region could have gained that advantage. The pull from every direction would have nearly balanced. Matter would have continued thinning as space expanded, and darkness might never have gathered into distinct sources of light. But if the original fluctuations had been too large, matter might have collapsed too early, creating a history entirely different from the balance that allowed stars, galaxies, and planetary systems to appear. The universe we observe lies between those possibilities, imperfect enough to create structure, but not so chaotic that every structure was determined during the earliest moments. Within the human body, heavy atoms were created by generations of stars that lived and changed long before Earth formed. But the path leading to those atoms began much earlier. A star could produce carbon or oxygen only after gas had gathered deeply enough. Gas could gather only in covered cowations, and das covered, and das halos could grow, only because the early universe preserved tiny fluctuations in density. In that sense, every atom carries more than the history of a star. It also carries the imprint of the cosmic web, of invisible gravitational wells, and of a slight unevenness that existed before light could travel freely through space. Today, telescopes look toward two widely separated ends of that history. The cosmic microwave background preserves an image of the ripples when they were still very young, while light from billions of galaxies reveals how those ripples developed into structure. Between these two ends lies nearly the entire history of the visible universe. Increasingly precise measurements may show how well the current model describes that journey, or they may reveal a subtle difference, suggesting that dark matter, dark energy, or gravity itself still contains an aspect we do not fully understand. Science does not need to know in advance what the answer will be. It only needs to measure the evidence carefully enough for the universe to place limits on the stories we tell about it. Beyond us, galaxies continue to move whether anyone is watching or not. Small groups still fall into clusters, gas still flows through halos, and stars still form before returning material to space. Meanwhile, sufficiently distant regions continue to be carried farther apart by expansion, gradually dividing gravity's construction into increasingly isolated domains. The universe has not become still, but the cosmic web's most vigorous era of growth may already lie behind it. What remains is a long age in which existing structures continue rearranging the matter within them, while the greater expanse of space quietly opens farther. And as the night becomes quieter, we can hold on to one final image of this entire journey. Not the image of a brilliant explosion or an enormous galaxy, but of a tiny ripple within a universe that had no stars. No one looking at it then could have recognized the galaxy clusters, planets, or a world with oceans waiting in its future. But across billions of years, gravity patiently followed that small difference, drawing matter toward matter, deepening every dense region, and slowly turning possibility into structure. The universe did not become a place of stars and galaxies, because it began in absolute perfection. Every light in the sky, every atom in the body, and every question ever asked by a human being could exist because, from the very beginning, that perfection was missing one very small part. Thank you for spending this quiet time with the sleepy universe. Beyond the window, the sky still carries light from structures. Gravity began building, long before Earth appeared. And as you drift more deeply into sleep, that immense network continues to unfold silently in the darkness, preserving within every point of light the story of how an almost uniform universe learned to take shape.